Great. I would like to thank the organizers for giving me this opportunity to talk about the BSM opportunities at the LHC. Especially thankful for the TAO and the PHENO team for organizing such a lively event in this special time. Okay, so following the great example of our first speaker, that he found his last time attending PHENO was 2010. This is a photo of me in 2010, was actually my first PHENO. You can see time has changed. I become a more symmetric person with a growing gravitational charge. But in the meantime, I hope to observe that there's a paradigm shift driven by the successfulness of the LHC. Back then, we worked more on models solving multiple puzzles of nature at once. But for now, we are working on models solving greater or equal to 1 puzzles, but more importantly, raising new features, signatures that can be probed by experiments. The logic behind is really because the Large Hadron Collider experimental colleagues have been working very creatively on the more established model paradigms. They provide us steady and impressive progresses all the time. And the series, our job becomes to identify opportunities that are missed or overlooked, important questions that could be answered, and to identify new interesting questions about particle physics. Having said this, it may sound like we are opportunists, right? But the real logic behind our shift of focus is driven by this common understanding of where the physics opportunity is. We all recognize physics opportunities are on this testable land that work on the intersections between the theoretically plausible series models and the experimentally accessible data signatures and the parameter space. And by saying by focusing on opportunities, we don't mean that we are passive people in the casinos waiting for the spinning table to settle down, but rather we are sailors trying to sail around and open new territories. And following this exact understanding of the current status of our field and our job, I organized my talk as the following. Okay. BSM at LHC is a very vibrant field. I can only do a very selective representative BSM opportunities at the LHC. I will divide it into 3 parts, maybe talking about the opportunities around the Higgs boson. Then I talk about our efforts in going to the more and more exotic signatures. And finally, if time permits, I will mention a few more recent fun ideas. Okay. So the first part is around the Higgs. The reason we think the opportunities are around Higgs because there's no doubt there are many big questions of nature are centered around Higgs, whether it's a fundamental or composite, what's the nature of the electric phase transition and its connection to matter-antimatter symmetries, and it could also be a portal to the whole new sector of physics. Higgs physics is and will be the central topic for the current and the future Collider program, and as reflected in many of the talks in this symposium, and especially in tomorrow's talk by Christopher Grosjean about future programs. Okay, the first example I want to give about opportunities is about starting new effects around the Higgs. Again, there are many different examples, such as the high energy, the multi-boson processes at high energy beams, winning over electric precision measurements, and many others. But here I want to talk about interference effect, which plays a special role in the recent progress of our explorations of Higgs physics. Here's the back then, 2015, our anticipation of the heavy Higgs coverage in this scenario of the minimal supersymmetric standard model in this famous MA tangent beta plane. We can see we have a vibrant program focusing on different types of Higgs physics, such as heavy Higgs decaying to tau-tau, covering the large tangent beta regime, and charged Higgs and light Higgs searches covering low tangent beta regime. There's also a precision program as well. But here's a very recent updates from Shufang Su et al. About the neutral Higgs landscape in this MA tangent beta plane in type 2 2XW model. It's a slightly different scenario, but the coverage are similar. Okay. I want to emphasize, of course, it's a very rich map thanks to our experimental colleagues' efforts, but there's one important improvement that I want to emphasize here is in this heavy Higgs but low tangent beta regime, which is only enabled, our knowledge here is only enabled by the most recent search carried out by the CMS for heavy scalar decaying to TT bar. This, to many people's surprise, this is the first direct searches for heavy scalar resonance decaying to TT bar. And one may ask the question, it's a resonance search. We should have done this long time ago. Why do you claim this is the first one? When we ask that question, we have in mind the resonance search, the simple search that for standard production of the heavy Higgs from a gluon fusion process decaying to TT bar. After subtracting the dominant background from the many different channels of TT bar resonances, we will be able to see a bump signal from the differential distribution of the TT bar invariant mass. But the reality is, the signal we should be looking after for a heavy Higgs signal injection will be a very special shape. For a CP even scalar, it will be a bump and dip around the mass pole. And for a CP outer scalar at the 550 GeV benchmark, it can be almost a pure dip. Okay. The physics driving this is a very special kind. That is only, it's driven by a special interference between the signal amplitude and the background amplitude, enabled by the following two facts. First, the background amplitude is a huge non-surprised tree-level process. Two, there's a non-trivial relative phase between the signal and the background amplitudes that one can see coming from this triangle diagram once using the optical theorem, that once you go across the TT bar threshold, this vortex gain a strong phase with respect to the background amplitudes. This was first discussed in the context of the standard model physics, Higgs physics in '94 by Scott Williambrook et al. But by the recent collective effort of the community, we understand how robust this scenario is, and with improved calculations of the effects and research proposals, that we are able to develop an updated understanding of this seemingly simple resonance, but in reality very difficult searches that need to make full use of differential distributions. And this drives the most recent change in our understandings of Higgs physics. But this is not a standalone case. This special on-shell interference effect is non-factorizable into a signal production decay calculation. One to have a full-fledged exclusive process to take into account the interference. And it helps us to gain new information about the width and phases and provide us interesting tests for interference. For instance, even for the standard model Higgs that we discovered in the diphoton resonance channel, there's an important on-shell interference effect that changes our prediction in the diphoton rate by about -2%. That is ongoing studies and improvement by many of the calculations. This can help us understand the Higgs waves better in a complementary way to other probes. Or for BSM physics, for instance, for heavy scalar decaying to a di-Higgs process, there are 3 diagrams interfering with each other, so the pattern is very complex. But we have our common Bragg-Wigner resonance here in the sine curve, and the on-shell interference piece can boost the cross-section by up to 40%, changes our anticipation and interpretations of heavy scalar resonances into di-Higgs. Help us understanding the important model that can play critical role for the strongly first order electric phase transitions. Okay. Now, let me switch to a second example of new opportunities around Higgs. We should start thinking about beyond the vanilla modes, that is standard search channels, and thinking more on the Higgs boson as portals to hidden sectors. Here's the bigger background is that we shall view the high-lumen LHC as the fest of statistics. Many processes that are statistically limited will gain huge from the upcoming runs of the LHC, including both the high-energy tail ends of searches, but also for those especially weakly produced processes searches. The example I want to give is viewing the heavy Higgs as a portal to the supersymmetric sector. It can help us once you start thinking about those modes. It can serve as probes of heavy Higgs bosons, but also can be the discovery channel of those SUSY electric states. And this also applies to many other general classes of BSM models. For instance, we all have the natural SUSY spectrum in mind. We have LSP being the BNO-like, and we have the Higgs xenos not far away from them as NLSPs. So in this MA versus the Higgs xeno mass plane, we can see to the left of this dashed line, this is the cross-section you gain from production to heavy resonances and decaying back to the electroweak and back to the LSPs plus Z boson. The color means the cross-section in units femtobar, but to the left of this dashed line, that means this new production mode of Higgs portal having a higher cross-section than the inclusive electroweak pair production rate. Okay, so from rate wise, one can already see the heavy Higgs can be a competitive, can provide competitive modes. But even to the right of this panel, even though they have lower cross sections, but because it's a heavy resonance, there's an intrinsic energy scale associated with those signatures, especially with the visible energy part of the Z boson, that can help us pick out the signal. For instance, if we work out a one benchmark model for this MA tangent beta plane that we saw earlier, we can see once you think about having as portals to electroweak and conduct such a new search, you will be able to cover a 2 sigma level at the high-lumen LHC to the left of this, this green line. Okay, this is in very complementary to the existing tau search and the future projections for the tau search. And for the bottom low tangent beta region, this is the 4-top search, and this newly facilitated TT bar line shape searches. We can see it provides a competitive and nice coverage of this infamous wedge region and has excellent discovery and exclusion potential. This is just one example. There are many other examples that we don't have time to go over here, but I list many of the reference here. And importantly, if we come back to the electroweak pair parameter space, this is the LSP mass versus the NLSP mass, we can see there's a difficult regions where the mass gap of around 100 GeV, because the background is huge from the inclusive Z boson processes and W and Z processes, and the improvement for them is going to be very slow, even with the high-lumen LHC, because they are more systematic dominated. So such new considerations of the portal channels will be able to improve our coverage up to about 450 GeV. So providing very nice complementary coverage to electroweak physics. So having enough about the opportunities around Higgs, and I would like to go to the exotic frontier in the second part of my talk. So first of all, we are more and more motivated to consider hidden sector physics. It's related to the new wave of thinking about the landscape of BSM models. So as particle physics has gone through a very successful exploration of unifications. We have electromagnetism, later unified as electroweak theory. With QCD, we hope they can be unified as grand unified theory, and we are even looking forward to unifying with gravity in the far future. Okay. But it seems the quest has been going to higher and higher energy and look for a more and more unified theory. But no one would ignore the big elephant in the room, that is the existence of dark matter, who have about 5 times larger radical abundance than our luminous matter. And it's hence generic and reasonable to consider the dark sector can have complex dynamics, even though the dark matter candidate itself may be the lowest lying state in this whole dark sector. But the generic dark matter physics can have rich interaction structures, mass spectrum, and can be unified with us as a theory at a higher scale. But at the current stage, the more important question for us to ask is beyond gravity, what are the hidden messenger fields and how we can seek for them? And there's from a generic field theory EFT point of view, we construct the portal couplings through the singlets, gauge singlets of standard model fields and dark sector fields, okay, which are colored in red and blue respectively, and the small parameters are labeled in epsilons. This also forms the basis of many discussions of low energy, high intensity experiments. But collider, I want to emphasize here, a lot of activities recently at colliders have been focusing on those possibilities because they will provide very crucial and unique complementary information in the GeV realm. 2 examples I want to give. One is, we all know, motivated by the strong CP problem, we anticipate one of the elegant solutions is the axion as the radio excitation of the QCD axion potential that relaxes the strong CP angle and give us the consistent measurement of neutron EDM. Okay, but such a solution can have axion potential, can experience new contributions in the potential. And those new contributions to axion potential in general will not be aligned with the QCD potential and undo the dynamical solution of the strong CP puzzle. So many of the recent model building effort has been focusing on how to impose, with model building tricks and actual symmetries, how to ensure the extra contributions to axion potential is aligned with the QCD theta angle, and thus making the axion solution more robust against other contaminations, so usually dubbed as Planck slopes. But the more details is not the focus of today's talk, but the consequence of such efforts often results in reinforced axion potential and, okay, that allow me to show these slides, and the heavier axion mass that more corresponding to the QCD primes confinement scale. So once you start to think about the possibility of heavy axions, we see a unique space and pose us new challenges. For the details of which of our solution, one can go to Sabik Kumar's talk in this afternoon. But the idea is, once you start thinking about heavy axions, we have a lot of active program from astrophysics and cosmology, and also collider and beam dump experiments covering those regions. There's a big open and well-motivated space that remain unprobed by the collider program. In fact, it should be uniquely probed by collider program, but for now we don't have effective coverage. The reason behind is such an axion is a very challenging signal. It's a light, rarely produced hadronic state, and is buried under QCD backgrounds. So once identify such opening opportunities, one realizes that with the decay constant of around the PeV scale, the axion can become metastable and travel a certain distance, then decay, allowing us to pick them out of the QCD overwhelming QCD background. Yet the decay constant is small enough that we have, thanks to the large gluon PDF, we can produce them sufficiently. So with our estimate, we can cover this regime as a first attempt. But being an optimistic person, we think the improvement of collider searches for prompt signals will be able to cover this regime. And our future activities in collider and beam dump experiment will cover this regime, and the Lonely particle will cover here. We can form a very meaningful and coverage of those well-motivated axion parameter space. Second example is the neutrino question. We know the neutrino mass has been a puzzle. The smallness of neutrino mass has been a puzzle of the standard model. And there's a nice testable neutrino mechanism called inverse seesaw. That is where the neutrino mass is corresponding to the following composition of the low energy interactions of stereo neutrinos and with our standard model neutrinos. Okay. This is a testable scenario, but there are remaining problems or problems with the smallness of many of the parameters. To explain the smallness of the neutrino mass, one still need to invoke, even though we have GeV or TeV scale right-handed neutrino, one still need to invoke small parameters such as mu and lambdas, which control the portal coupling of the stereo neutrino to standard model sector, as well as this lepton number violating couplings. Model building efforts has been given to making the stereo neutrino composite. This gave us the freedom that those operators can come from the high scale operators that is as a high scale deformation of the CFT that later through dimensional transmutation generates a small scale and effectively generates a small effective couplings that controls the IR behaviors of the inverse seesaw mechanism. But a new phenomenology coming from such a scenario will be a very astonishing signature of producing stereo neutrinos in the shower. I can have a double boson decays into charged leptons plus this whole sectors of composite states and generating very unique collider signatures that can be opportunities of the future. Okay. But you can see many of the hidden sector considerations gave rise to the sector series of signatures called the long-lived particles. Okay, what is long-lived particles? Here's a typical event display of a large of the LHC event. So we collide proton beams at the center of the detector, and we produce tons of particles with a very dedicated detector. We record a lot of the information here. Okay. Long-lived particle is a particular set of signature, BSM signature, that the mother particle travels a certain distance microscopically and then decay back to the standard model so that they can be captured by our detectors. When we built the LHC, we didn't have those long-lived particle signatures as the primary physics goal in mind. So such signatures receive difficulties. It has triggered problem that we may not record them fast enough, reconstruct them fast enough, so we don't record them. They have trouble with simple reconstruction algorithms, and it's hard to estimate the non-standard backgrounds for those signatures. But it is the exact reason of those difficulties drives the recent interest of the community in long-lived particle signatures, because we may have missed those great opportunities for discovery if we don't look for them. And there's a nice community review about the status and the recent development. In fact, the LC program become very rich at this point in searches for long-lived particles, overcome many of those difficulties already. But a series can also contribute beyond identifying those opportunities. For example, we realize that not only those particles, long-lived particles, give us displaced vortex, which is a major focus and a major tool for us to select them out of the QCD backgrounds. But the fact that those heavy particles travel a certain distance then decay means they will be obviously delayed if we time the signal compared to their standard model background, which travels at the speed of light. using such delayed information, one can carry out a general classes of searches for delayed Lonely particle signatures, which I don't have time to go through, but I hope you can go check my backup slides where we show the very exciting recent results from CMS in carrying out the first delayed jet analysis for Lonely particles. But secondly, there are many more ideas enabled by the upgrades of the LHC. For instance, as mentioned in Anali's talk, one important upgrade for the LHC for CMS is this high granularity calorimetry detector. Okay? Before this, usually in serious eyes, the calorimeter is a perfect absorber of energy. So they record one-dimensional information about the energy deposition at a particular location. However, with the high granularity detector, where we have inserted many layers of high resolution silicons plus scintillators, we'll be able to see the hits in the calorimeters. Even though they can be clustered, one can still reconstruct exactly these different the shower tracks from the energy depositions there. That gave us milli-radian spatial resolution and 30 picosecond temporal resolution. Not only that, this detailed calorimetry information allows us to have the jet and shower substructure reconstruction. And those information are passed to low-level triggers, exactly solving the trigger problem for Lonely particles, and gave us a great improvement in the potential coverage for the high Lonely particle signature. For instance, if one work out the benchmark model of so-called neutral naturalness, where the Higgs boson decay to a pair of hidden glue balls, which come back to standard model through mixing with the Higgs into jets. So this is an example of Higgs decaying to glue balls, which decay back to standard model. Those jets can be captured by this high granularity calorimetry. Even from their shower shape, we'll be able to resolve their constituents direction and reconstruct the displaced vortex and also the delayed signature. We'll be able to improve our current coverage of the already very rich program on Lonely particles in neutral naturalness by orders of magnitude to 10 to the minus 6 level. And providing very complementary information about the Lonely particles compared to other subdetector searches, such as the muon spectrometer searches by Atlas and prompt Higgs to 4B searches by Atlas. I also want to emphasize there's a very recent CMS displaced vortex result came out yesterday that shows us very nice coverage of the Higgs to hidden glue balls in this realm of centimeter level lifetime. So we can see it's a very vibrant program that has driven a lot of new thinking about how to search for them. In fact, to overcome those difficulties for Lonely particle signatures, there's a lot of ongoing efforts trying to expand the LHC program. Many of them propose auxiliary detectors of the LHC, such as Methuselah, Codex B, Alex3X, Anubis, Phaser, Model, Millikan, etc. There's also a series of beam dump type of experiments providing complementary information about the light Lonely particles. So the list has been growing, and the program become more and more rich here. But I want to highlight one of the programs, which is the Phaser program, which has already been funded, and the phase 1 is being installed, and they don't stop there. In fact, from Felix Kling's very nice talk yesterday, that there's a new expansion of the Phaser program trying to detect the high-energy neutrino interactions produced from the LHC, which is also funded and being installed. That's going to give us unique understanding of neutrino interactions in the TeV realm. And other efforts, there are several other experiments who have collected their demonstrators data, and we kind of anticipate some of the results come out soon. Okay, so for the sake of time, I just want to have a quick mention of the having more fun. And a more important direction is to have fun in BSM particle physics search. That I don't have time to go to the details of each example because they are more scattered around, but here's my personal list. I think given the rich spectrum and complexity of possible BSM signatures, model agnostic searches that enabled by the recent machine learning development can be an important tool in addition to our current program. There are many talks in the MC for machine learning for jets meetings, and also there's even a quantum version in one of the parallel talks. This is under name of anomaly detection. My take is there's no perfect anomaly detection algorithms. However, if one combine enough anomaly detection algorithms, one would have a rather comprehensive coverage of the BSM signatures. But more than that, we should open our mind. As I mentioned earlier, we can try to define non-traditional collider goals and asking more fun questions. For instance, we can ask, can we see color flows through the interference effects of the hadronic antenna pattern? Or can we define new metrics for the machines so they can compare or detect events in a more effective way, and also for us to be able to define the metric space for series with the interface of machine and data. And there's important open data that allows us to answer some of those or start to demonstrate some of these non-trivial questions asked about the colliders. For example, we can ask if we can learn QC from data using machine learning, or we can use the open data trying to overcome some of the difficulties in understanding the lonely particle non-conventional backgrounds which is not described by the common generator. You can search for true muonium and the quark signatures, etc. The program is very rich. Okay, so I don't have time to cover other important topics in my mind for BSM opportunities, but flavor physics, QCD, electric precision, machine learning, they all have their own unique roles in our explorations of BSM physics. And a quick review of what I covered in this talk, that in my mind, the upcoming opportunities of at the LHC will be around the Higgs. And we can enrich a program by going to exotic signatures. And what's important is we should have fun and ask interesting questions. Stepping back a little bit to the bigger picture, the success of the LHC and the standard model has triggered a paradigm shift already. This means new chances for us to define questions and quests, with testability being the backbone there. And our work as a community will be less like a boson, which means there won't be an overdensity for a given topic, but as a reaction, we should start to appreciate researches not of our immediate research interests. But what hasn't changed is that we are still driven by curiosity, and the BSM opportunities at the LHC reside in our own creative work. And I hope we all enjoy our explorations as endeavors to open new territories. And thank you for listening to my talk.
Thanks, Zhen, and thanks for the nice coverage of all the BSM search at LHC, which is almost mission impossible. Mm-hmm. And he also make his talk very interactive with annotation, which is a good thing I learned. Okay, there's several questions for you. The first one is, it's in the Q&A. The first one is from Chris. Could you elaborate on the hopes and expectations that might result from long-lived particle search?
This is a great question. Let me see if I can give you a quick example. So obviously, there's a risk we're still driven by our big questions of naturalness and also around Higgs. One interesting solution is so-called neutral naturalness, that we have Higgs hidden sector strong dynamics. Well, the Higgs is a portal to the dark hidden sector, and the hidden sector particle, which is a 0++ state, will mix with our Higgs and become a long-lived particle. So those efforts in trying to cover this lifetime versus branching fraction is maybe the new signal is here. With our improved efforts, we'll be able to make discoveries here, which will be of the detailed studies of this property. We'll be able to understand what's the relevant hidden sector dynamics and what's the next predictions of new physics nearby, maybe at 5 TeV scale also. But we should have in mind the goal of our BSM searches is not to exclude new physics, but to discover new physics. And those coverage plot, even though they are plotted as exclusions, but the hope is to discover. And afterwards, we'll be able to do a second step, which is to diagnose the BSM discovery, which can go to many different directions. It can be neutrino-nitrogens, or it can be axion-like particles, or it can be stereoneutrinos, etc. That link back us to the big questions we have been always after.
Okay, the second question is from Carlos, you know who. It's about the Higgs. At the low tiny beta, it seems like one could profit from the production of neutral charge Higgs in association with top and bottom quark, which has no interference effects. Could you comment on those channels?
Sure, this is definitely a great question. So in fact, it's really a multi-channel search program. As we see here, the charge Higgs are produced in association with bottom and top quarks, but the coverage is in those yellow color that is in the back. They do have a complementary coverage in the low tangent beta regime. However, as I mentioned, this TD bar search covers this regime already with the current 100. I forgot whether 40 inverse femtobar or 130 inverse femtobar. In fact, the future projection of them grows, let me see, of those TD bar channels, which grows further down to the higher and higher masses through a rather conservative projections by me and my collaborators. And the 4 top channel do avoid the interference effects. But the 4 tops production rate drops faster as your heavy Higgs goes to higher and higher masses. So those regions will be covered by the 4 tops. As you see, at about 500 GeV, they're actually better than the TD bar search. However, the cross-end drops so quickly, will soon be dominated by this TD bar search that one has to take into account of those interference effects.
Okay, then there's 3 more questions, but I would ask you to be relatively short for your answer given the time. Okay, the next one is from Lientao and ask you to comment on the axions. For the signal of heavy axion, does it has to be the one that's solving the CP violation, strong CP problems, or it can be a generic axion-like particles?
To answer it shortly, it doesn't need to be the strong CP solver axions, but it can be a generic axion-like particles. And what we want to point out is, although we often say axion-like particles and write down the axion EFTs, so long as there's no big hierarchies between the scales of the axion operators, coupling gauge bosons, coupling fermions, coupling Higgs, the hadronic channel will always dominate. And that is the big window that is open there and being unprobed. And we hope to bring emphasis to this challenging regime and hope our experimental colleagues can take up this challenge and cover this well-motivated regime. Okay,
the next one is from Linfen, and Zheng, I said short answers. More details on the HGCal improvement of the LLC detection. Why is the limit so much better improved compared to the previous one?
Great. So let me answer it quickly. The HGCal, the first thing is HGCal has its own trigger. So you avoid about the factor of 2 order of magnitude the rate loss from the traditional triggers. If we have a time-based trigger for Lonely particle signatures, for heavy enough hidden glue balls, you will have comparable coverage as what I showed there. However, the current searches are not based upon the time delay, but rather based upon the traditional trigger and the displaced vertex search. which each give you the trigger give you 2 order magnitude, and the vortex reconstruction limits the effective volume where you can collect signal, and actually enlarge such volume by about 1 order magnitude. Together, they give you those 3 or 4 order magnitude improvement. And again, I want to emphasize, we didn't assume full efficiency. We pay about 1 order magnitude of efficiency loss from various reconstructions, and there are further room to improve.
Okay, the last question, you only have 30 seconds to answer. It's from Matthews about the status of the phasor neutrino measurement.
Great. I think the more detailed answer will go to Felix's talk, but I think I was very impressed by that talk, so I put his slides here. Let me see. So basically, it's being funded, and they are constructing this phasor neutrino expansion by a combination of private and public foundations. And they will be able to measure the neutrino interactions with the neutrino as a function of neutrino energy in this TeV realm that is uniquely produced by the LHC, complementary to the accelerator data here and the ice cube measurement. In fact, to all 3 different flavors of neutrinos. So it's a very acute expansion, and we do anticipate new results coming from that once we turn on the LHC.